Good afternoon and welcome to the first Jones seminar of the spring term. It's good to see so many of you here on such a fabulous day, but the sun's going down later, so I'm sure you'll have a little bit of time to enjoy this fabulous weather that we're having. Today we're fortunate to have Steve Megli here to talk to us. He's Vice President and General Manager of Assembly Test Manufacturing at Intel. He's responsible for managing Intel's assembly and test operations worldwide, which includes facilities in Costa Rica, the Philippines, Malaysia, China, and Vietnam, and maybe he'll share his frequent flyer miles with me. He joined Intel in 1987 as a process engineer and has held various positions in the organization. Before that, he was at Delco Electronics Corporation. He received his degrees from Southern Illinois University and has received both the Intel Achievement Award and the Intel Quality Award. Today he's going to talk to us about innovation that moves the world forward. Please welcome Steve Megli.
Thank you very much. It's terrific for me to be here today. I'm really excited. I got to tour the labs today, and I must admit I'm a little bit out of my element. We're pretty far removed from academia, as you'll see as we go through. But as we were putting the foils together, I do think we got one of them right for this audience. And so with that, I'll just start with a little word from our sponsors. I always worry when I see those in the Intel meetings, and Deb Conrad, our director of marketing, shows this in one of our Intel meetings. And everybody laughs. I'm going, that doesn't mean anybody else in the world is going to get it, Deb. It is. We have a lot of those actually, and if you go on YouTube, you can find a bunch of them. You kind of do Intel sponsors of tomorrow, you'll see a bunch of them. I think we covered this. Like I said, this is a little bit about me. I got a couple of degrees in engineering. From a very small university, a long way from Dartmouth. I've been in this industry about 27 years now, mostly in engineering and all of it in high volume manufacturing. So I know that here, a lot of people are here. If you think I'm going to come tell you about the latest research and the latest breakthroughs we have in our research labs at Intel, first thing I'll tell you is I won't tell you that because I don't know, and even if I did know, I couldn't tell you that. So hopefully we'll be able to make it the afternoon interesting, even talking about a little bit more practical applications of the technology and the methodology that we use at Intel to really drive the innovations that we start in places like the research labs at Dartmouth into very high volume, and what the business model that we use to drive that is. A little bit about Intel. So we are the leading manufacturer of electronic components worldwide. We have about 300 facilities. We're represented in 50 countries. Our revenues last year were just north of $37 billion. Again, that's a worldwide globe that we serve. We've had 22 consecutive years of positive income. About 80,000 employees, and if you look at the demographics of our employees, of that 80,000, about 43,000 are technical degrees, and you can see the breakout, about 12,000 master's graduates, 4,000 PhDs, and 4,000 MBAs that work in finance to tell us that we're spending too much money. Our brand is very recognizable. I think, even the little jingle that they sang at the end of that commercial is one that everybody knows. It's one of the top 10 most valuable brands, and it's been that way for a long time. So we've worked really hard on the brand, and that continues to pay off. I'll talk a little bit about more towards the end of my talk about what we're doing in corporate social responsibility, but we do invest over $100 million every year in education, and this is education at all levels, from elementary school in developing countries to collaborations with large universities on fundamental research here in the U.S. We are the single largest purchaser of green power in the United States. This is something that is becoming more and more important, and you may have seen yesterday that we actually changed our corporate charter statement to include this idea of corporate social responsibility and sustainability. It's good for our business, but it's also just good business for all of us to do. And the other thing that really makes me the most proud of working for Intel, you wear a lot of hats, but several times a year we put on blue t-shirts that say Intel Volunteer, and we in 2008 said that we wanted to, for our 40th anniversary, do 1 million hours of community service, and we actually did about 1.3 million hours in 2008 of Intel employees going out in their local communities and just trying to enhance that community and give back for all of the things that we need to do in those communities and make the world a better place. What does Intel do? Well, our core business is supplying the microprocessors for in the Intel architecture for the computer market. So if you see in the middle there, that's the kind of the client and server business. That's the core of our business. We make microprocessors, the i3, i5, i7 are today's marketing names for those, for the laptop mobile market, the desktop market, and the server market. We've been doing that for many generations, and it has been the core. It started back in the IBM 286 days, and it's really continued ever since then. So that is the core of what we do at Intel. We drive the process technology and the design architecture to make that happen. What we're seeing, though, are really 4 key growth areas. So like I said, we're just about $40 billion, and the thing that the stockholders ask us is, where does the next $40 billion come from? We think that there are actually $10 billion opportunities in each of the 4 areas. This idea of handhelds, and this is kind of a ubiquitous device, maybe a smartphone, maybe something lower than a netbook, and it's changing all the time. So that space is still being defined. But we think if we can get a device in there running on Intel architecture that has the full internet experience plus all of the other features that we want to have that device do, there's a big opportunity there. Consumer electronics is a very old industry, relative to what we're doing. But if you think about the digitally connected home and having a TV that also is your internet engine and instant access to whatever that media that you want to interact with is, whether it's the internet or a movie or a television show, we think there's a large opportunity in that space for us. Netbooks is really one that we talked about as an opportunity 3 years ago, and it's really become true. It's not 10 billion yet, and we still think there's a lot of growth. But an idea that I have a specific small form factor derivative of a PC, if you will, that I can carry around easily, that's very mobile, that allows me to do the tasks that I need in everyday life. I need to surf the web. I need to do my email. I maybe need to work on a PowerPoint presentation. Not powerful enough to do video editing or high intensity gaming or something like that. But really, that market has we really established that market over the past 2 years, and it's become very widely accepted. And the thing that we were worried about, and everyone asked us about, is, was it going to cannibalize up into the notebook part of our business? And the answer to that is no, because they're really different applications. Most people who go buy netbooks are buying it as their second or third machine. So this is one that was kind of on the opportunity list that we've done very well in going forward. And the 4th area we think is another $10 billion opportunity is this embedded space. And this is a lot of small specialty businesses where if we have a small, powerful core that's based on the Atom processor, we can provide a solution into that space. And this ranges everywhere from infotainment systems in automobiles, if something that's more than a GPS that you can interact with safely in your car. Things like digital signing. I don't know, I didn't look here, but if you drive down the freeway in Arizona now, I would say 15% of the road signs are now digital, and you have to have a processor to control that. There are other automotive applications such as brake systems and stuff like that. So the embedded business for us, if you look at our balance sheet, has grown steadily, and we really see some exciting possibilities in the near future. Beyond that, we think there are emerging areas. Digital health is one. The health industry costs are a lot of times driven by the technology. And we think that if we could get some standards into that space, along with some hardware into that space, that this is an opportunity not only for Intel to grow, but to really reduce the overall cost of healthcare going forward. NAND memory is one that we are now turning a profit on that we think is going to grow. Anyone that's had a chance to take a PC and take out a hard disk drive and put in a solid state drive, and you realize how much of the time you spend computing, you're waiting for that drive, it's quite incredible. And so we think that there's expansion opportunity there. And then things like WiMAX and visual computing to make computing available everywhere. We think that those are other emerging growth areas for us going forward. What I'm going to talk about is really the combination that's all supported by our employees, but it's the combination of silicon process, and when I say silicon process, I mean both silicon and the packaging process, the platform architecture that we design in, and then this idea of going out and creating markets through establishing standards and collaborations that are needed to standardize and grow the business in the future. So a little bit about where we are. We are worldwide. You can see the locations marked in yellow on here are where we have our fab operations. Most of our research and development is done up in Oregon in the D1C, D1D, and components research area. So that's kind of the core of where the process technology comes from. We have large fabs in Arizona and New Mexico. We have a fab that's running our 130 nanometer technology down in Hudson, Massachusetts. We have 2 fabs in Ireland, a fab in Israel, and we are going to open in the second half of this year a fab in Dalian in China. Assembly Test, which is the business that I've been managing for the last 2 years, you can see that we have a large facility in Costa Rica. In Malaysia, we have both Penang and Kulim, a very large campus there, about 10,000 employees there. And Chengdu, China, is again a very large revenue runner for us. And then we're opening again in the second half of this year a new factory in Vietnam. So I'm happy to sell frequent flyer miles, and I'm not so happy to get any more. People ask me where I am. I tell them to call United Airlines. They'll be able to find me because I do spend a lot of time crossing the Pacific in my workday. So. This idea of being kind of a global business does have some specific challenges. I think in many of the places where we're going and doing businesses, we're going into places where the environment is dominated by old industry, and we're bringing in high-tech, leading-edge technology. That really does challenge us in many areas as you look at it. Places, controlled countries like China and Vietnam, you have customs regulations, you have government regulations, both on the United States side and on the receiving country side. The skill set of engineers, the skill levels of engineers in this job, one of the things I found is the wide variability of the skill sets. I'm happy to say that the U.S. Education system is still number one. I would say that unequivocally in the engineers that I deal with. I would say, however, that there's a few people breathing down our necks, and places like China where they're so hungry for technology, they're graduating a far larger number of engineers than we are, and the capability continues to improve year after year. So we expect to see that trend continue. And also when you go into these places, there's just no infrastructure, suppliers, applications, people to come in and work on your tools is very difficult. A lot of times we go into emerging markets because if you're there in your manufacturing operations, you can sell there. And the bottom one is something that we worked very hard on, in this idea of corporate social responsibility. But you go into societies where corruption is the norm, and you have to go in and say, that's not the game that we play. So if you want to have Intel there, we expect a different result. And that does present some challenges in doing business in those countries. Just talk about technology. This is the core of our business model. I could talk about, I could tell stories about manufacturing all day long. It's obligatory if you're an Intel employee and you do any presentation, you have to include Moore's Law. Gordon in 1965 actually wrote this on a napkin. And there's a great controversy because I was at an Intel conference and someone put this foil up and they said, Gordon said that the number of transistors would double every 2 years. And the way they had it staged, Gordon was sitting in the back and he stood up and he said, I didn't say every 2 years. He said, I said every 18 months. And it actually depends on which one of his publications you look at what the answer is. But we've established it now as 2 years because that's what we set our corporate goals on. And so whatever it was in 1965, it's 2 years today because that's when we deliver our technologies. But the fundamental economic law behind this is the engine that has driven Intel. So if I can double the number of transistors periodically, I can put twice as many transistors on the same size die, or I can cut my cost and put the same number of transistors on a die that's half as big. And the economics of that are pretty simple. And if you lead in this space, and you're first to market in this space, and you can supply then products that have differentiating features, then you're going to win. And that's Gordon, who's actually one of the nicest people you would ever meet in the world, established the law, and it's really been the core of what drives our business at Intel ever since. So for 41 years we've been doing that. I'm happy to report today that Moore's Law is alive and well. When I joined Intel in 1987, there were pundits out there that said, we're not going to be able to get beyond 1 micron. These were very, well-established, reputable people that were in different fields. They said there's a physical limitation, the wavelength of light, whatever it is. And that was, 25 years ago. And you can see that we have established that Moore's Law is alive and well. From 180 nanometers in 1999 to 32 nanometers, which we launched and are running in high volume in 2 factories, soon to be 4 factories today. And we have a clear pathway in 2011 for 22 nanometers. Now, one of the questions is, where does it end? I got asked by a couple of the students today, and the answer I'll give is a little bit evasive, but it's kind of the right answer is, when innovation ends, then either Moore's Law or some derivative of Moore's Law will end. And if you go talk to the folks that work in our components research organization, what they will tell you is, hey, you know what, 20 years ago, we had about a 10-year vision of how we were going to continue Moore's Law through the, we were trying a bunch of different things, and we knew some of them would work and some of them would, but we had about a 10-year look. And if you go talk to them today, they'll say, we got about a 10-year look into the future of how to continue Moore's Law. So when they start saying, oh, our runway is getting shorter, then I will get nervous. But I will tell you that over my career, the thing that has amazed me is our ability to stay on this track by not simply doing the same things over, faster, smarter, but really through just amazing innovations. And then applying those innovations practically and taking them to very large volumes to drive the economic engine of the company. So we are on track. We are now, if you go buy an i5 or an i7 processor, and if you don't have one, please go buy one this weekend. That's a 32 nanometer processor. And then in 2011, we are on track to start producing 22 nanometer products. I want to talk about kind of one thing that I think differentiates, and this might resonate with some of you, in the way that we develop and take our products to high volume. That's quite a bit different. The traditional method is really smart people in places like Dartmouth do research and they publish their results and the fundamental science breakthroughs happen. And then someone else will take that and develop a prototype and says, I can take that fundamental science and I can build one of this device. And then someone in high volume manufacturing will say, well, if they can build one, let's go develop and build machines to build 100 or 1,000,000 or whatever that scale is. And what Intel's method is really kind of we merge those together. And so the fundamental research is done in collaboration, both at Intel and in collaboration with universities worldwide. But the research is not done until you can show the practicality of doing it at a high volume. So if I have some breakthrough with a thin films, putting some thin film on some layer that I need that helps me. Basically, I'm not done until I at least have a machine that's demonstrated that can run a significant amount of volume and do that on a bunch of wafers and not just one piece of silicon in a lab. And so what we really do is in one sense, we keep the research engaged up until the point where we show feasibility of not just prototypes, but of high volume prototypes. And then we go into development where we really start to understand, what is the variability of that film across the wafer, what are the defects that tool generates, whatever those are, and the development of that into then a high yielding medium volume kind of process. And those facilities you saw in Oregon, they're not our biggest factories, but they run a lot of silicon, and they run them. Their job is not done until they get this thing to high volume at very high yields. And then we transfer that out of our development facilities into our manufacturing facilities. And we don't just say, here's the recipe. We use a process called copy exactly, and there have been many, many master's theses written on this, but I will tell you that the subtlety and the integration of our processes is almost mind-boggling, and it's unbelievable. And if we didn't say that everything has to be exactly the same on that tool sitting in the manufacturing floor in Arizona as it is in the development line up in Oregon, we would get no yield on our wafers. And I'm completely convinced of that. I have a lot of war stories about copy exactly things that we learned along the way. And some people say this isn't innovation, but I believe that it's one of our strongest points of innovation in the company. My favorite story is when we were doing the 65 nanometer process transfer. It was working great. The development guys had done their job. We had a high yielding process. And I was on the receiving end, the factory in Arizona. And we had a defect that they didn't have. And it was causing our yield to be, at least half of what theirs was. And so we had a problem. And it was a defect that it took us about 6 months to figure this out. It was an airborne defect that somehow was, there were some contaminants in our air that weren't there in Oregon. And so we were, first we blamed the dairy cows that were on the lot next to us. Turned out that wasn't true. We started looking at weather patterns. It seemed to be worse at night than it was in the day. But the fundamental root cause solution to that is pretty incredible if you think about it. The fact of the matter is, in our factories, we control the environment to a very high degree, temperature, humidity, contaminants. And in Oregon, because if you think about it, Oregon, it rains all the time. They dehumidify the air to get it to the humidity spec of the factory. In Arizona, it's very dry. We humidified the air to get it to the spec of the factory. The air in the factory was actually the same humidity, but it turns out that the dehumidification process was scrubbing this contaminant out of the air in Oregon. And so now if you go to our fabs in Arizona, you'll find out that we humidify the air above with spec and then we dehumidify it, just like Oregon. And that is what copy exactly looks like. We've got case study after case study where 3 inches of stainless steel line meant the difference between a product that worked and a product that didn't work. 3 inches of stainless steel vacuum line feeding the tool. So when you think about innovation, a lot of people look at copy exactly and go, that's not innovation, it's just got to be the same. But the innovation comes into the way that you measure it being the same and the degree of detail that you have to go to for it to be the same. So this looks pretty simple on this graph. I will tell you that we put thousands and thousands of man hours into that transfer. And so what you now have is kind of this seamless route that goes from basic science to manufacturing these things at high volume. And the fact that we can then start our manufacturing at very high yields means that we can bring products to the market like the i5, i7 in just huge quantities almost instantaneously. And if you think about the business process of ramping up a factory, almost instantaneously, this factory always starts at the same yield that this factory is at that day. And so before that, we would always kind of start from zero again. And so copy exactly is an innovation, I think, that is probably one of the core advantages that we have at Intel that other companies haven't really quite figured out. And a lot of people say, well, we can't quite do it that way, we'll copy smart. Well, when you're talking about the humidity of the air in Arizona, there's not a lot of people that are that smart. And so that's really a key innovation for us. Our silicon technology, I wish I could talk more about it. Working at Intel, the IP systems that we have are very robust. I know what I need to know about the process technology, and that's, since I'm in a packaging end of the business now, that's not much. I could tell you if I could tell you something about our 65 nanometer process, but so I'll give you some generic overview. So in the 80s, we basically used 11 elements to build our transistors. In the 90s, it went to 4 elements, and you can see now we're pretty much using the entire periodic chart. And I will tell you that this shows my age a little bit. In Southern Illinois, when I looked at a periodic chart, it didn't have all that stuff on it in 1985. So, but the use of materials and the materials science and the small doping levels of this, and we announced when we did 45 nanometer the high K metal gate. That is a great example of development of a process all the way through, and it's much more complex and integrated than it ever was, and it was really hard to do this before. And then economically, once we depend so much on that cycle from development to high volume, that economically we place huge bets on that cycle. So if you know about 32 nanometer, I talked about we just launched into production. A year ago, think about where we were in the worldwide economy a year ago today, right? A year ago today, no one was feeling very good, and there was, this is the worst recession ever. When's it going to end? Is it going to bottom out? And a year ago today, we bet $7 billion that 32 nanometer would work. We didn't have a working design. The process development wasn't complete, but we knew that we had to make that bet. So what Intel does on that every 2-year cycle is we make these huge bets on that technology lead. Now that puts a tremendous amount of pressure. That's why Moore's Law is now every 2 years, because that's what we have to do to recover this economic bet that we make. So every 2 years we make a huge bet, and 45 nanometers was 2 years earlier. It was a little less because the process complexity was a little less. I think we did $6 billion on 45. And so when you look at this, the reason that you do that is because fundamentally it's a very capital intensive industry. The bet that you make, the big outlay that you have to make are for the tools to run these processes. They have to be very high volume, defect free, integrate all of those basic sciences in the high volume in a very uniform, across the 12-inch wafer. If you think about that, what it takes to do that is very, very expensive. The big driver of this, as everyone knows, is lithography. The lithography equipment to shrink that transistor every 2 years gets very expensive. But you really do have to retrofit almost every tool that you have every 2 years to make this work. We use about 70% of the tools that we use move forward to the new technologies every generation. And this is the bill on top of that. And so last year, when everything was awful, we made a $7 billion bet, and I'm happy to say, if you watch the news these days, that and hopefully, I'm not going to make any comments about earnings because I'm an officer and I would get arrested. But you saw our Q4 results, you saw our results in Q3 of last year, and this bet's going to pay off, and it's paid off every time for us over the past decade. I want to move a little bit now to out of what's traditionally called silicon and talk about packaging. 2 reasons for that. One is it's the world that I manage now, so I have to talk about it. The second is that I actually think that this is the next inflection point for our industry. What you find is that you remember I talked about those growth products, right? Things like MIDs and smartphones and tablets, and what you see if you just look across the bottom of this graph, and there's just a different grouping of different in-use devices, and then the thickness requirements for those devices. And so if you start to think about it, now it's not just having the silicon that wins the deal for you, it's having the silicon in the right form factor. And for many of our small form factor products, we actually grind the wafer down to where if I held it up, it would look like a piece of paper in here, and I could make it that flimsy. I mean, we make it that thin to get into these kinds of form factors to serve these kinds of devices. my favorite example of this is everyone remembers when Steve Jobs held up that manila envelope and pulled out the MacBook Air, right? It was a famous introduction. Everybody went crazy. I was in the middle of this one, and the differentiator in this case was not the silicon. The silicon was basically the same silicon as we had, but we basically got a call from our CEO, who I guess had lunch with Steve and said, you got 6 months to make this form factor work. And we won that deal because we said yes to that form factor, and then we had to go make that work. And if you look at it, behind the wall, and when Steve did this introduction, is what the normal form factor was and what we were able to do in just a few months. And so if you look at the requirements on the bottom, on the right is the thickness of a nickel, and across the left are the thicknesses of some of the packages that we're going towards. And what I will tell you is that as we continue to look at smaller and smaller devices, our gadgets are getting smaller and thinner, and we're as human beings obsessed with that. But this is, we're coming to a break point of the current technologies and the current the science that we know, and this is all going to change, is my prediction, in the next 10 years. And I was talking to Dr. Sullivan, and I think one of the things that we should stop thinking about is where is the die, and then the package, and then the silicon, because I think that's all going to morph together. I think that the package is going to become an extension of the die and some subpart of the PCB as we go through the next 5 years to make these form factors fit into the devices that we want to carry around on our daily basis. So I think that this is a very exciting area for us, and it's one that we're spending a lot of time thinking about. And it's not just that the devices have to be thinner and smaller, they have to be thinner and smaller at higher performance levels. So this is just a graph of what we see, the first layer interconnect, the interconnect between the die, and what we call today the package on many of our devices. So the I/O requirements are becoming higher and higher. The pitches are becoming smaller and smaller. And so, we used to do wire bond on the bond pads around the outside of the die. We no longer do that. We now use bump technology. But bump technology, the bump has a certain dimension, and you have to be able to solder it, and it has to then not short out with the next bump, and we're really running up against that. So we're probably going to have solderless technology. We're probably going to have to make connections with things like through silicon vias to attach our memory packages, stacking a die on top of each other with fundamentally no space or interposers between them going forward. So, and then where this all comes together for Intel is what we call the Tick-Tock model, and I'm not sure where this phrase got coined, but this is, we talk about silicon. I talked a lot about silicon process technology every 2 years, and so what we do is every 2 years, when we get a new silicon process technology, we fundamentally shrink the microarchitecture and take advantage of that scale. And then we can, it's less cost, and you can go drive profits that way. And then in between process technology changes is where the design guys come up with their microarchitecture changes. And so you have process technology, a year later microarchitecture, a year later process technology, a year later microarchitecture. And this is the business driver. This is what keeps us a generation or more ahead of the competition. And we do this in all of that client space. So it's every year you're going to see an innovation. And we're not doing that to make it obsolete. We're doing that to continue to drive the technology and drive the capability of the products so that we can serve different kinds of markets. But you can see that this started, in Marome on 65 nanometer. Right now we have launched Westmere on 32 nanometer. And sometime next year, you'll see our Sandy Bridge technology. It'll have a different name. These are all internal code names. They'll probably be called i5s and i7s as well. And you can see that that's the model. And what we found was the risk of process technology innovation was great, and the risk of microarchitecture design innovation was great. And it was really a bad idea to put those on top of each other. And that's why we stagger them. If you remember in the early 2000s, we kind of had a hiccup in our technology lead, and it was because we tried to stack two of these on top of each other. And that's when we really firmly established that you're going to do this idea of a Tick-Tock, and you're not going to do them at the same time. And so it's a yearly innovation based on two independent 2-year kind of cycles, one in design and one in process architecture. Okay, I want to just finish, and then I'll take whatever questions, and we'll go wherever you guys want to go with this. I want to talk about kind of what I think is a very important in the corporate world, an emerging trend, but also the right thing to do, and that's really corporate social responsibility. And I think that this is becoming moving up the scale from something that you did because you were required to do it to something that corporations have to become the leaders of. And in many, many areas, not just in what you build as a corporation, but what your entire supply chain, you have to go manage that. And this is something, like I said, yesterday we added it to our charter statement. It was something that 5 years ago, basically NGOs would drive governments to make laws, and then governments would try to impose those laws around the world on corporations. And what we're seeing now is that is actually flipping over. And that companies, if you want to be a company that's a viable company, that the shareholder requirements now include things like green power, corporate social responsibility, managing your supply chain to make sure there's no corruption up and down your supply chain. So if you remember, an example of this, if you remember that periodic chart and all of those elements, a year ago it became apparent to us that we had to go make sure, and the good news is we found out that we were okay, that through our entire supply chain of all those elements, we had no conflict metals. I don't know if you know what conflict metals are. Those are metals that are mined in Africa by companies that basically use slave labor to mine them. And so we had to make sure that none of our suppliers or their suppliers, all the way down the supply chain to the mining industry, were clean and not using conflict metals. And this is becoming a requirement. And as you're publicly held, stockholders are holding a higher and higher bar to you. And so what Intel's stance is instead of waiting for that to happen, we think we ought to flip that over. The corporation needs to be a leader in that, and then we need to drive the NGOs and partner with the NGOs to make sure that we are leading that. Because if we wait for the NGOs and governments to lead, it will be much slower, as we've seen in many other processes, than we are today. So we really have 3 or 4 different areas that we work hard on this. The first one is advancing education worldwide, really the next generation of innovators. And this is something that we spend a lot of time in. Investing in education programs. We sponsor the world's largest and oldest science fair and science awards. It used to be the Westinghouse Science Fair, now it's the Intel International Science and Engineering Fair. We've sponsored that for 10 years and just announced we're going to sponsor it for the next 10. We teach teachers to teach using technology worldwide. We've given this training to over 7 million teachers in 50 countries across the globe, and it's teaching them how to use technology and use that to make them more effective teachers at all levels of education. Advancing technology, access to technology. We've got a classmate PC, looks like a lunch pail. People can pick that up. We've developed PCs that operate off of a car battery because there are rural places in India where people are they're starving to get into the digital world, but they have no power, no reliable power. So we've set up kiosks where we have car batteries, and we've connected the PCs into those. And in China, we've done the One World Ahead program, actually across Asia, but predominantly in China, where we're putting PCs in classrooms all across the rural areas where people this is their only chance to get in. And so really trying to work on the accessibility. And then strategic alliances and advocacy, partnering with people like Dell to say, let's reduce the total emissions of our combined processes by 50% in the next 5 years. And so I think that there are, across this idea is, education is what got us to where we are. We are an engineering company, and we have to have that next generation. Environmental sustainability, so responsibly managing our operations. It takes much less water to make a chip today than it did 10 years ago. Some of that's because we changed the technology to use less water. Some of that is because we've refined our facilities for better reuse, using water 100 times instead of 1 time, things like that. Eco-smart products. with the invention of Core a few years ago, 3 years ago, we really stopped saying it's performance at all cost, and we started saying it's performance plus power. And so what we're generating is a world that uses much less power to do the computing that they need to do. And then some collaborative initiatives around the environment. And I think I mentioned on the first foil that we are the U.S.'s largest consumer of green power. And that's to make that industry viable and to make that industry go, and so that we can all benefit from that going forward. And then finally, corporate citizenship, the foundation of business ethics and compliance. With the scandals of 5 years ago, the Enrons of the world, I've always felt like Intel was the most integrous company I've ever been associated with. But making sure that you have those systems in place so that's true for everyone. Innovating in our communities. I talked about volunteerism. I talked about working in the schools. And then really flipping that thing over so it's not the NGOs becoming the leaders of corporate social responsibility, but inviting other corporations to come along on that journey with us. So, if I can make this work. So kind of in summary, we're, at Intel, we're on a mission. We have to have flawless, timely execution to Moore's Law. We have to make that work. That drives our business model. And it's not really, just corporate and making money. We really think that we are changing the world with the products that we deliver. And I had lunch with a few of the students today, and it's just incredible to me the technology of education and how much different the technology of education is today than it was 10 years ago. And if you feel like you're part of something that's enabling a different world, the connectivity that we have just in the meetings that I sit in every day with people from Vietnam and China and Costa Rica, and the technology we use to drive that, the connections that I've been able to make, hopefully other people see that. And it's not just that we're trying to make chips and make a buck. I mean, obviously that's part of our corporate charter as well, but it's really changing the way that people live through our silicon and packaging technologies. Doing that while we're reducing our impact to the environment and to change the world both today and tomorrow. And so one of the things we have at Intel is it's not just what we make, it's what we make possible. And before I take questions, we'll have one more quick.
Tiny little thing. Okay, I found it. Okay.
We are Intel, sponsors of tomorrow.
So with that, I'll conclude. I'll do my best to answer any questions that you have.
Okay, well, I'll lead off.
Okay.
I will ask if you can make an estimate. If you assume that, say, 10% of Intel processors that have been sold are out there operating, what is the power consumption of Intel outside of the fab lines and test facilities and everything else? I mean, do you have any sense for this? I don't, but I hear rumors of Google is locating their places next to power plants because, there's some of the grid jobs and things like that.
Yeah, so it's a really fascinating question, and it's really kind of what drove Intel to say it's not just computing speed and power, or computing speed, but it's a combination of speed and power. And we do have we do have a sense of that because we know for each product that we build, we can go do the math and say, if you assume that this many are out there, this is what microprocessors are consuming. I do know that with the left-hand turn that we made with the high K metal gate process, it's a 3-year payback. You can buy all new servers in a place like a Google Farm or something like that. You can buy all new servers, and in 3 years, you get your money back by the money you save on electric power. So it's something that we recognize, and we also recognize that we were a source of this non-green, the computing power, and we said there has to be a better way to do that, sustainability. So each process technology node not only has what's the transistor size that we have to deliver, and when do we have to deliver it. But we're now putting power and also other environmental impacts like water, chemical usage, waste out of our product into each of our processes. But it is something that we're concerned with, and it's something that we think our products are really starting to answer more and more of that question than they have in the past.
Looking at Moore's Law, you make a convincing case for having kept Moore's Law over a remarkable span of time, but you were just talking about making a turn in a different approach. It seems that for power reasons, and I think for interconnect reasons as well, the focus has gone from increasing the number of transistors on the chip to keeping the number of transistors per core relatively constant.
Right.
And increasing the number of cores per chip. Is this a trend that's going to continue for the next 10 years? Is there another change coming?
No, I think that is the trend. I think you can say, okay, I'm going to run multiple cores, and then in our case, we're saying another important part of that is for a given number of transistors, most of the time they're sitting there idle. So how many threads can I run through that processor at the same time? So I think we'll be able to continue on Moore's Law for a while. I don't know when it's going to end. I mean, it's a great question. But I also think that the improvement that you're going to see in computing performance is going to continue because we're going to innovate other ways to get that, through that Tick-Tock model, and not get it all just from the number of transistors, which was kind of what we did in the past.
How much can Intel drive that continued innovation if it has to come on the software side and the compiler side rather than being on the technology side?
I have to be careful about the words I use. I think we are a very strong player in the infrastructure of the business, and I think if we can show that there's a good business case, then you will find the people that are writing that software to do that. I think the other key is to really allow use the open architecture idea and allow some of that innovation. You'll see on the Atom processor that we just started this apps site. If you have an iPhone, you can get lots of apps, but if you're a developer, you don't really get access because it's not open. For netbooks, we're starting some of that. So hopefully, we can influence the ecosystem, if you will, because we are an important part of that ecosystem, to start to look at that and make suggestions about here's a better way to do this. Here's a better way to here's a better way to get power out of the device that we just showed you, computing power, if you will. Yeah.
Are we seeing the same thing in memory? Now when you can buy a terabyte for $100 retail, is that the same Moore's Law type of situation like that?
Yeah, Moore's Law has driven that industry, and because that industry is so commoditized, Moore's Law has probably driven it harder than microprocessors, if you will. I mean, it's very competitive. The technology there has not been so much total performance, but really just driving on size. And so Moore's Law has been a driver of that. We're starting to see now, though, some multi-state memory technologies, and so can I get more virtual memory, if you will, out of the same number of transistors. So you're starting to see some of this other innovation as well. But memory has been driven probably as hard as anything by the Moore's Law technology, because if you can be the first to that next node, and you can be the first guy to sell that terabyte at $100 and make a profit, because I'm pretty sure the one you bought, they probably had a loss. But if I can get to that next node and make a profit, then that's a big advantage for those guys. Yep.
Considering all the idea of driving up the number of cores, how much does Intel spend compared to other corporations and even its own hardware design line in terms of compiler and language design to help there to be manageable threading?
If I got your question right, I think this is the answer. I think we're spending a lot more today than we did 5 years ago. I think we've really recognized the importance of that part of the ecosystem. We now have Renee James, who sits on the Paul Olini staff, driving software and innovations. We've made some key acquisitions in that space. So I would say probably it was something we didn't worry about. If you would have asked me 10 years ago, oh, there's other people who worry about that. We think that in many cases, software, I talked about packaging being the differentiator. Having the software is really what drives the market. I talked about market creation. And it used to be that when you came out with that latest, greatest processor on that new technology, everybody wanted one, you know, the Wintel argument. The Wintel argument is not nearly as strong as it used to be. So there are many other kinds of application specific. And so we've recognized that, and we've substantially added to our investment in that in the past 2 years.
Okay, I think if there are other questions, we'll be here for a few minutes and we'll have the speaker again.
Thank you guys very much.